In this video, we're going to start Chapter 2. We're going to cover Section 2.1 and a little bit of 2.2. This chapter is about summarizing data. We're going to learn how to calculate some statistics for a data set. Suppose you have a random sample of 25 college students and you ask them how many hours per week do you typically work outside the home? And let's say this is the data we collected. So as you can see, I have 25 pieces of data. I have the number 0, which is 0 hours per week. Somebody works 15 hours per week, and so on. How can we summarize the data presented here? How can we summarize and analyze it? What kind of information can we extract from this data? So one thing we can do is make a histogram. A histogram is a bar chart that's associated with numerical data. So to make that histogram, the first thing we want to do is sort the data. We're going to put that data from smallest to largest. I went ahead and did that right here. And by sorting it, we can see how much of each number of hours students worked. So for example, there are 3 zeros, so 3 students out of the 25 worked 0 hours. There's 1 5, there's 4 15s, and so on. Now that same data is presented here visually in the histogram. So you can see my first bar says 0 hours, and there were 3 students who worked 0 hours. We have 1 student working 5 hours, 4 students working 15 hours, and so on. Now we tend to do this with a spreadsheet, and I'm going to teach you how to do this with a spreadsheet in the next video. But right now we just want to understand how this works, how we can make a bar chart using the data. Now notice that I have a prominent bar, the tallest bar, and that corresponds to 30 hours. In the histogram, I can see something called the mode, which is the most common piece of data in the data set, and that is 30. So the mode is 30 hours. Now this is a piece of information that summarizes the sample. Remember, this is a sample of 25 college students. So this is a statistic. It's a piece of data that summarizes the sample. The mode is one way to measure the center of the data set, where like the majority of the data is. Now another way to measure the center is to find the median. The median is where we organize the data from smallest to largest, and we pick the number in the middle. Okay, so I have, let me just go back to this slide here. So I want to find the middle of this data set. Now there's multiple ways to do it. So the middle of the data set is like folding the data in half and getting that number that's right in the middle. One way to do it is to cross off the first number and the last number, and then cross off the second number and the second to last number. So like cross off 0 and 40, then 0 and 35, and 0 and 35, until you reach the middle piece of data. Now that's fine, you can do that, but it would be easier if we had a formula to get there quicker. And here's the formula. You take how many pieces of data you have, and you add 1 to it. And then you take that number and you divide by 2. So here I have 25 pieces of data. I'm going to add 1 and I get 26. I divide 26 by 2 and I get 13. So what I'm going to do is I'm going to take the 13th number. So instead of looking to the left and to the right and trying to find the middle term, I'm just going to count to 13 and I'm going to take that number. The 13th number has 12 pieces of data to the left and 12 pieces of data to the right. And that is the median. The median is 25. This is another statistic. It summarizes the data here. Now, 25 pieces of data is an odd number, and an odd number of data has a middle. Sometimes we don't always have a middle, and that occurs when we have an even number of data values. So what I'm going to do is I'm just going to add an additional number to this data set so that you can see what to do when you have an even amount of data. So I just threw a number on the end, the number 42. Now we're going to follow the same formula. We're going to take how many pieces of data we have. So I added one additional number to this, so that's 26 pieces of data. And I'm going to add 1 to it, which I'm going to get 27. And then I'm going to divide by 2, and I get 13.5. So that means I have to go a little bit past the 13th data value, halfway between the 13th and the 14th data value. So the 25, the first 25, if you remember, we circled it, that is the 13th data value. And then the 14th data value is also 25. So I want to get right in the middle of that. And what I'm going to do is I'm going to take those two numbers, the 13th data value and the 14th data value, add them together and divide by 2. So since they're the same number, if I add them together and divide by 2, I get 25. So that is the median, 25. So in this particular example, the median was easy to find because the 13th data value and the 14th data value are the same. But let's say that the 13th data value was 25 and the 14th data value was 28. What we would do is we would take the 25 and the 28, add them together and divide by 2, and that would be 26.5. So that would be the new median. That's if the 13th data value was 25 and the 14th was 28. Okay, let's go back to the original data set. I just added this 42 to show you how to work with an even amount of data to find the median. So we're going to cross it off and go back to the original. So we said that there are, so far, 2 ways to find the middle of a data set, the center, and that's the mode and also the median. There's one more way to find the center of the data set, and that is called the mean. And this is actually the most common way to find the middle of a data set when you have numerical data. What you're going to do to find the mean is you add up all of the data values together, and then you divide by how many data values are present. So I'm going to take, by the way, this is usually referred to as the average. Whenever you see the average is equal to this, they mean they use the mean to calculate the average. So what we're going to do is we're going to put these numbers in a calculator. So if you have a calculator with you, you can double check this formula. I'm going to take 0 and add 0 and add 0 and add 5 and 15 and so on, all the way until I get to 40. And then I'm going to count how many data values I have. We know that we have 25 data values. So we're going to take that sum and divide by 25. And you should get 22. So the mean is 22. Now again, most people nowadays, especially because we have usually a lot of data, we use a computer to find the mean, median, and mode. Right now, we just want to understand the principle behind these formulas and see if we can do it by hand. So I recommend that you try to put this in a calculator and see if you can get 22. All right, let's find the range. The range is where we take the highest or the largest data value and subtract the smallest or the lowest data value. So especially when the data is organized from smallest to largest, we can see that the one on the right end, 40, is the largest data value, and the smallest data value is 0. So we're just going to subtract the 2. When you do that, you get 40, and that is the range. The range is one way to talk about how the data is spread. So the range is also a statistic. It's a piece of data that summarizes this data set. Okay, let's look at that histogram again. There's a lot of bars here, and sometimes we want to simplify the histogram. We want to group similar values together so we can have less bars and simplify our histogram. This is called binning data. So bins are just groups of data values that are similar. So let me show you a couple ways we can bin data. So here's our histogram again. And now I have 4 bars. It's the same data, but with less bars. And what I did was I took all of the values between 0 and 10 in my original data set, and I put them into a group called a bin. I counted how many values were between 0 and 10, and then that's the first bar. I had 4 pieces of data between 0 and 10. And if you look at the original histogram, you can see we had 3 values that were 0 and 1 value that was 5. And I believe that was all of the numbers less than 10. So those 2 bar graphs kind of joined together to make 4. Then I went and counted how many values I have between 11 and 20. And I made this bar here. And it turned out that I have 7. You can see the height of the bar is 7. So there were 7 data values between 11 and 20. Then I counted how many were between 21 and 30, and how many were between 31 and 40. So all of the same data is presented here, but we can kind of extract some new information. We can see that the same amount of pieces of data, there's 4 pieces of data that's between 0 and 10 hours, and 4 pieces of data that's between 31 and 40. So we have the same number of people in the sample that were working between 0 and 10 hours as were working between 11 and 40 hours. We also see that the majority of these college students were working between 21 and 30 hours. Here I have binned the data into 0 to 20 and 21 to 40. So you can see now that maybe you're interested in whether students are working part-time or full-time, something like that, depending on how you want to bin the data. Here, I think most college students, the university would like them to work less than 20 hours. And so you can see in this particular example, we actually have more college students working between 21 and 40 hours in the sample than between 0 and 20 hours. But they're kind of close. It looks like between 0 and 20 hours, there's 11 students, and between 21 and 40, there's 14 students. So the bars aren't exactly the same height, but there's not a drastic difference. So there's different things you can get by reducing the data into bins. All right, I have another example for you. I have that Sarah and Katie record their 10 best times for a swimming race. What I would like you to do is pause the video and see if you can find the mean, median, and mode for each swimmer. Okay, this is what I have. I have that Sarah's mean is 70.9, her median is 69.5, and her mode is 75. While Katie, her mean is 78.9, the median is 79, and the mode is 79. My next question is, on average, who is the better swimmer? Well, if you look at Sarah's mean, median, and mode, all of them are lower than the mean, median, mode of Katie. Now, when you're swimming a race and you're recording times, the person with the shortest time is the better swimmer, right? So if this happened to be, let's say you were recording meters instead of time, you wanted to see over a particular amount of time, how many meters did you cover? Well, then you would want the person with the highest meters. But because we're working with time, the lowest time would mean they're faster, so they're the better swimmer. Now, when we use the word average, we're typically talking about the mean. So whenever I say on average who's the better swimmer, you're going to look at the mean and you're going to compare the means. And you see that Sarah's mean is lower than Katie's mean. But it turns out for each, the mean, median, and mode, Sarah's always better than Katie when it comes to swimming. Okay, find the range for each swimmer. And whose times would you say are more consistent? So pause the video and see if you can find the range. So Sarah's range is 15, while Katie's range is 25. So it turns out Sarah is more consistent because the spread between the times, Sarah's times, is 15 seconds, while the spread between Katie's times is 25 seconds. So you can see Sarah tends to swim around the same times, a little more consistent with her times than Katie is. So the following frequency histogram represents the IQ scores of a random sample of 7th graders. IQs are measured to the nearest whole number. The frequency of each bin is labeled above each rectangle. Okay, so we have this histogram of IQs of 7th grade students. And you can see that we have bars, but the bars don't represent a single number. They represent a range of numbers. And if you look closely, it looks like the range of numbers is units of 10, right? And above each bar, we have a number, and that's just how many, because this bar graph is kind of simplified. Excuse me. It's hard to tell because there's tick marks of 10 for the frequency. It's hard to tell how tall a bar is, like what the actual number is. So the frequency is how many numbers between 60 and 70 occurred, and that is 2. Okay, first question. How many students were sampled? Well, all we have to do is add all of these numbers above the bars together. And if you do that, you'll get 200. Determine the bin width. So the bin width, we just mentioned this, is 10. That's the distance between the width of the bars. So the first bar is between 60 and 70. There were 2 people who had an IQ between 60 and 70, 3 people between 70, 80, and so on. Which bin had the highest frequency? So the bin with IQ scores between 100 and 110 have the highest frequency. That means that those are the numbers that are most common. It's the highest, most prominent bar. Which bin had the lowest frequency? Well, that's 150 to 160. What percent of students had an IQ of at least 130? So this question is asking you, how many students had an IQ score of 130 or higher? So when it says at least, that means the lowest number is 130. From the bar graph, we see there were 8 students with 130 to 140, 2 with 140 and 150, and 1 with 160. So if we add all of those numbers up, we get 11. So there were 11 students with an IQ of 130 or above. Now the question is not how many students, but what percent of students had this IQ. And what we're going to do is we're going to take the part over the whole. So we're going to take 11 and divide by how many students there are total, which is 200, and we'll get a decimal. And the decimal is 0.055. If you make that a percent, that means just move the decimal over 2 units and put a percent sign there. So it's about 5.5% of this 200 students had an IQ score of at least 130. Let's describe the shape of the distribution. So this distribution is not quite symmetric, but it looks almost symmetric, meaning that if I go halfway in in that tallest bar, halfway, and I put a line there and I fold the distribution in half, the bars are almost the same. Not quite, it's not perfect, but it is symmetric, or nearly symmetric. That brings us to our next topic, which is describing the shape of distributions. So one type of distribution you might see, so remember distribution, I'm using the word distribution, which just means a histogram with these bars for numerical data. Okay, so we're focused on numerical data right now. So when we have numerical data and we have a bar graph, let's say that looks like the one on the right, where most of the data is on the left, but then it starts to have a long right tail. So the tail determines what we call this thing, and we call it right skewed, meaning that most of the data is on the left, but it starts to skew on the right side. So there's a long right tail. Now, let's say this is the type of histogram we have on the right here that has a long left tail. We call this left skewed. So the bulk of the data here is on the right, but the tail is on the left. So that's what determines the type of skewness, and we say left skewed. And we mentioned this symmetric data. So symmetric data looks like usually like a bell. The most of the most of the histograms that we're going to see in this class are going to be bell shaped, like a bell that you ring. And you can see that this graph here, if we make a line in the middle, it's almost symmetric. It's not perfect. The bars don't exactly line up, but it's almost symmetric, and we just call it a symmetric graph. But there are other types of symmetric graphs, like this one. We call this one a uniform distribution. So if we had bar graphs that look like this, if we put a line in the middle, the left and the right side would almost line up. So we call this a symmetric distribution or symmetric histogram. Okay, here's a common question. If mean, median, and mode all measure the center, should they be close to each other? Should we be getting the same number for the mean, median, and mode? So it would make sense, and they are the same, if we have a perfectly symmetric distribution. So if your distribution, which is just another word for your histogram, so that bar chart, whatever bar graph you come up with, if it's perfectly symmetric, then the mean is the median, which is the mode. However, most of the time, if we get a distribution, it's not going to be perfectly symmetric. I would call that nearly symmetric. And if it's nearly symmetric, meaning that some bars on the left and right might be taller than the bar on the other side, then the mean is about equal to the median, which is about equal to the mode. So here is an example of a perfectly symmetric distribution. And notice that the middle bar is the tallest. That would be the mode. And it turns out that the mean and the median are equal to the mode. Now here is another distribution that's not quite perfectly symmetric. And this is heights of randomly chosen college females. And the heights are listed on the x-axis. It's kind of hard to see, but it's that's what it says. And you can see that it's not perfectly symmetric, but it does have a similar shape, an almost symmetric curve like the one on the left. It almost looks the same as the one on the left. And because it's not perfectly symmetric, the mean and median and mode are close to each other, but they're not quite equal. And here's one more graph. Again, this one is not perfectly symmetric, but it does have symmetry. The left and the right side kind of look similar. And this is just on the top, it says histogram of symmetric continuous. That just means it's a symmetric graph that is with a continuous variable. We've talked about continuous variables like measuring height or weight or something like that. So it's just some variable that's continuous, and this is the histogram of it. And since it's not perfectly symmetric, you can see the mean and the median are not equal, but they're kind of close to each other. And the mode would have to be that tallest bar, which looks like is somewhere between 95 and 97. So the mode is a little bit further away, because I would say this graph is less symmetric than maybe the one on the left. So the less symmetric it is, the further those would be spread out. But all I want you to get from this is, if we have something that looks almost symmetric, then the mean, median, mode should be pretty close to each other. Now, if the data is not symmetric, if it has, let's say, it's left skewed or right skewed, then there may be some outliers. Outliers are data values that are far away from the rest of the data. So where the center of the data is, you may have some values that are far away. And this really affects the mean. It'll pull the mean away from the center. So when you have data, and we'll learn how to recognize outliers very soon, but when we have data that has outliers, then if we want to measure the center of the data, we tend to use the median instead of the mean. The median is not affected as much by outliers like the mean. So maybe here's an example. If you have some homework scores, let's say you're doing really well on homework. Let's just say that there's 10 homework scores in a class and you are making like 90, 100, 85, 95. Let's say 9 of those values are very high. And then let's say you missed a homework one day and you got a 0. That 0 is very far away from the rest of your homework scores. And if you've ever averaged them together with the mean, you'll see that your average is pulled down away from all of the other data values. So in that particular case, it's better to use the median because the median really shows the center of your data set rather than the mean. Okay, so we talked about symmetric data. Now let's talk about skewed data and what happens to the mode, median, and mean. So here I have a graph that if you don't focus on the words that say median, mean, let's just focus on the bars. And if we look at the bars, we can see that it has a right tail, which we said if it has a right tail, it's called right skewed. When the data is right skewed, you can see we have outliers. The outliers are going to pull the median, the outliers are going to pull the mean towards the outliers. If the outliers are on the right, it's going to pull the mean to the right. Okay, so you can see in this image, the mode is the tallest bar, but the median is a little bit to the right of the mode, but the mean is even further right to the mode. So whenever we have right skewed data, the part that I really want you to focus on is the relationship between the median and the mean. The mean goes to the right. Well, when we have numerical data, the right side are bigger numbers. So the mean is going to be bigger than the median. If we have data that's left skewed, if you look at this graph, you can see that the middle of the data, I guess the tallest bar and where most of the data is concentrated is on the right, but the tail is on the left. Okay, what's going to happen? The mode is going to be in that tallest bar. And then the data on the left is going to start pulling the median a little bit to the left, and it's going to pull the mean even further to the left. Okay, so the data values are going to start, the data values are going to pull the mean in particular to the left. So what I want you to focus on, maybe not so much the mode, but the relationship between the mean and the median. The mean is going to be less than the median. And that's because when we're working with numerical data and we're pulling the mean to the left, the data values are getting smaller. If you look at the number line, the number 20, 16, 12, those are the numbers going towards the left, they're getting smaller. So the mean is less than the median. All right, consider the following data sets. So I have 3 data sets, and just take a look at them real quick and kind of get an idea of what numbers we have here. Like the first data set has a bunch of 7s, and the first number is 1 and the last number is a 13. And then in the second data set, we have about 5 7s and some other numbers and 1 and 13. And then in the third data set, we have 3 7s, and again on the ends is 1 and 13. What I would like you to do is see if you can calculate the mean, median, mode, and the range. So pause the video and see if you can do that real quick. So the mean, median, and mode for all of these pieces of data is 7. What is the range? 12. If you take the largest data value and subtract the smallest data value, you get 12. Now, are these data values in the data sets, do these data sets look the same? No, right? I would say that the last data set is spread. There's more spread away from the mean of 7. Things are spread a little bit more than the one in the middle. And the one in the middle, the data values are spread more than the first one. In other words, you can see that there's a lot of 7s. If I was to make a histogram of the first data set, I'd have a really tall bar with 7s, and then I'd have two bars, one at 1 and one at 13, that only have one data value. While in the second one, I'd have a little bit of a shorter bar at 7, some more numbers, um, a bar at 8 that has a height of 2 and a bar at 6 that has a height of 2. And then on the bottom one, I'd have more spread, like things are more spread out. So the height of the 7 bar is a little bit shorter, but then I have some other numbers showing up. Now, how can I describe this with a number? Like mean, median, and mode describe the center. They're telling me the center of the data set. That's something we're extracting from the data set. And the range tells me from the smallest to largest, that kind of spread. But there's a different type of spread here, which is the internal spread. How far away the numbers are from the mean. And that is called standard deviation. So we're going to learn one more number that summarizes the data. It's a statistic called standard deviation.